Welcome to the Explainer. Okay, today we're diving into something really wild. We're looking at a fascinating intersection of disciplines, specifically how an abstract geometric concept literally solved one of the most notoriously frustrating physical limitations in all of computer science, the system crash. It's an absolutely brilliant example of theoretical math coming to the rescue of concrete code, and I can't wait to get into it.
Here's our roadmap for today. First, we'll hit the Stack Overflow problem, then look at how you actually patent math, explore Pythagorean topologies, unpack the recursive dialectic formula, visualize non-halting tiling systems, and finally, we'll rethink infinite recursion entirely.
All right, Section 1, the Stack Overflow problem. Let's talk about the physical limits of modern recursive software.
So I want you to consider this fundamental question. What is the exact difference between an infinite loop and a system crash? I mean, in theory, an infinite loop just runs forever, right? But in reality, on actual hardware, an infinite loop very quickly turns into a system crash. Why? Because while theory doesn't have physical limits, your computer's memory absolutely does.
Think about standard recursive programming. Deep queries are massive space hogs. Every single time a function calls itself inside a nested loop, the system allocates a memory stack frame. It's kind of like dropping a physical breadcrumb every single time you take a step into a maze, just so you can find your way back out. If that maze is infinitely deep, well, you're eventually going to run out of breadcrumbs. In computer terms, this linear increase in memory creates a catastrophic vulnerability.
And this brings us to a quote that hits home for literally any developer out there. When the stack becomes full, the program will crash and you will have an error. The notorious Stack Overflow. Finding a way to execute these deep recursive queries without hoarding memory, creating a truly memory-free recursive solution, isn't just some neat parlor trick. It's absolutely critical for building infinitely scalable databases. Which brings us to Section 2, patenting abstract mathematical ideas. If the solution to this physical hardware problem is just a math formula, how on earth do you patent it? Well, the USPTO has a very specific process for this, one that was explicitly updated to handle critical new technologies. Step 1 is simple. Evaluate if the claim recites an abstract idea, like a math concept. But if it does, you don't just stop there and reject it. You move to Step 2A, Prong 2, which says you have to evaluate if the claim, as a whole, integrates that abstract exception into a practical application that physically improves how a computer functions. So the takeaway here is that math by itself, totally unpatentable. But US Patent 12664142, developed by Kyle Smith, flips the script. It proves that a formula is eligible if it physically improves the machine. His Hierarchical Script-Database is the bridge. It takes abstract mathematical geometry and applies it to physically eliminate stack exhaustion during deep recursive queries. Let's break down exactly how it pulls this off.
Moving right along to Section 3, the Pythagorean tree topology. This is the mathematical bedrock powering this patented database engine.
Before we get into the really complex topologies, let's just ground ourselves in the base geometry. You probably remember this from school. A primitive Pythagorean triple is a set of three coprime positive integers, a, b, and c, that satisfy the famous a squared plus b squared equals c squared equation. And coprime just means they don't share any common factors other than 1. This incredibly simple, ancient geometric relationship is actually the secret key to mapping modern data.
Now here's where it gets cool. Back in 1934, a mathematician named B. Berggren discovered that every single primitive triple in existence descends from one single root node, the 3, 4, 5 triangle. From there, they branch out infinitely into a ternary tree using three highly specific deterministic 3x3 matrices. Because this math guarantees an infinite tree with zero collisions or duplicates, Smith's database assigns every active data node a coordinate on this exact tree. It means the database can route queries algebraically, totally eliminating the need for massive memory-heavy index directories.
And that sets us up perfectly for Section 4, the recursive dialectic formula. This is the engine controlling how these nodes spawn and scale.
This right here is the mathematical novelty at the heart of the system, the recursive dialectic formula. F of n equals 2b over a times f of n minus 1 plus f of n minus 2. It acts a bit like the Fibonacci sequence, a second-order linear recurrence relation. But instead of just adding the last two numbers together, it multiplies the previous state by a very unique parameter, 2b over a, which is derived directly from the legs of our right triangle.
To make this a bit more concrete, let's look at the fraction 5/6. If you want to keep recursive growth from blowing up your computer's memory, the system translates mathematical growth into decay. Say you have a growth rate of 6/5, you instead use its reciprocal, a 5/6 decay rate. And this specific 5/6 decay mathematically associates perfectly with the 60-11-61 Pythagorean triple.
So why does this matter? Well, this decay rate actually dictates the spatial and logical positioning of newly spawned data nodes. It literally reverses standard recursion. Instead of unbounded growth just chewing through your RAM, it uses the term x to the 1 to represent convergent nesting. The recursive calls get mathematically smaller, shrinking geometrically toward a vanishing point. This discrete scale symmetry acts as a built-in physical stabilizer, basically making sure the database can never exceed its bounds.
Let's translate that into physical space in Section 5, non-halting tiling systems.
If you want undeniable proof of that USPTO practical application requirement, just look at this comparison. Traditional recursive trees require linear memory allocation for backtracking. That's what risks the stack overflow. But the scale-symmetric Pythagorean tree computes paths dynamically in zero extra space, or O1 space as computer scientists call it. An infinite loop in the old system crashes the machine outright. In this new patented system, it simply compresses geometrically toward a vanishing point within a bounded spatial footprint. It's night and day.
To really visualize this non-halting tiling system, developer Kyle Smith gives us a great structural analogy. Imagine a parent rectangle that's 12 by 18. You can mathematically tile it with infinitely many smaller repeating rectangles, starting with a 12 by 10, scaling downward continuously along a number line. You are quite literally fitting infinity inside a finite bounded box. The math itself never halts, but the physical space it occupies never exceeds the borders of that original 12 by 18 rectangle.
But the real magic? That happens when the database has to navigate back up this tree. The old method hoarded parent references in the physical memory stack. The new method uses unimodular matrix inversion. Because the branching matrices we talked about earlier are unimodular, their inverses are perfectly clean integers. The database literally calculates its exact path backward, dynamically on the fly using math, completely throwing out the need to remember the path in physical memory.
Finally, let's wrap this up in Section 6, Rethinking Infinite Recursion, and look at what this actually means for the future.
Here is your big takeaway, and it's a total paradigm shift. By leveraging these geometric subdivisions, theoretical infinity can run non-haltingly inside a bounded computational window. The recursion asymptotically approaches a vanishing point. It executes continuously, forever, without ever consuming an increasing amount of your computer's system resources. It fundamentally solves the stack overflow, not with more hardware, but at a purely structural level.
Which leaves us with a pretty massive question to ponder. If integrating pure abstract mathematics, like primitive Pythagorean trees and scale-symmetric recurrences, can completely eliminate the physical limits of computer memory, what other fundamental software barriers are we struggling with today that are actually just geometry problems waiting to be solved? It's a thrilling frontier. Thank you so much for joining me for this explainer, and hey, keep questioning the limits of what's possible.